Yes, has updated itself. So, anyways, okay. So, maximal ideas in continuous functions on which space? Right. I am unable to. Right. Yeah, that's fine. Yeah, let's take closed interval. Let me turn on my video so that. Oh, ah. Oh, it is gone. That's very strange. Or maybe it is not. Oh, yeah, this new format. Ah, okay, video thing is of course here, but I don't see anything. Share, comment panel. So, do you see any video? Mm, no. Okay. I don't know because maybe with the whiteboard it goes out. Anyway, I've turned on my usual. But this is like the Google Meet thing. So, yeah, this is from Google Meet. So, anyways, that's not a big problem. Okay. And even this panel is open. I don't know. But, anyways, yeah. So, oh, now it doesn't write. That's the problem. Okay. Yeah, this is a update. Oh, I can't write anything. Add a page. Okay. Added. Now I try to. Oh, highlighter pen. Can't write anything. Yes, some dots I can make. It was writing, but now it's not writing. Okay, let me just close it. Otherwise, I will just do on Jamboard. Okay. Yes, now it works. Maximal ideas in sea of compact space. Okay, so this is a ring and it has an identity. Hmm. So, of course, you know that the maximal, I think you were saying this once, and at that time, I think, yeah. So, M maximal ideas are of basically this form, basically V of some x naught, right? F such that f of x naught is equal to 0. So, mhm, Right. So these are certainly maximal. That's fine. I am not proving that. Now, if you say that M is maximal, so let M be maximal. Don't know, we might need some more conditions. So we will certainly need X to be housed off. Yeah, I think. And since we are also, I mean, we will probably not need to assume compactness, but let's assume it and see. So you have a compact Hausdorff. Okay, so also for the time, let's assume that these are, this means continuous functions from X to R. Okay, it might happen that for C, the answer is different. Okay, so let me assume, I suppose this is what we were assuming implicitly anyways, but just making it, putting it there. So then you see F in M implies there exists some Y naught such that F of Y naught is equal to 0. Otherwise, just a minute. Yes, right. So it is fine. So we need to basically find out that X naught, but in this way we cannot say that Y naught is that thing, that all the things in M vanish at Y naught. We cannot say that. Yeah, I mean that is what we are trying to do in some way. Yeah. Right. So that's what. So that tells me the idea that basically you say that, okay, a given X in X, there exists. So if just can I scroll this? Just checking. Do you know if this can be scrolled? Yes, I have. I can add a page, but I would have liked to scroll it if possible. Yeah, then I will just add the pages. Okay. Yeah, so just like you said, right? So x if is not of this form, then what does it mean? It means that for every x in x, there exists fx in M such that fx of x is not equal to 0. So what can we do from here? So from here you would like to create an element which does not vanish anywhere. Yes. So yeah, there are several ways to go about it from here. So then it implies that there is ux, right? There exists neighborhood such that uh, not equal to 0, right? Greater than, uh, we will not need, I mean, you are right, exactly. So that's what we'll do. Yeah, but yeah, so for the time being, let's not, I don't think the modulus, so I'm just saying that this is, yeah, maybe how to write this? This is non-vanishing, right? Non-vanishing. Uh, Anyways, that's clear. Mm-hmm. Yeah, right. That's right. Finitely many UX which cover it. But then so what? Right. Oh, okay, right. So you want to say then you want to take some sum of squares or something. Yeah. Right. And this will be always positive. Right. Yes. 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 Right. So this is clear, right? That this function will be always positive, strictly positive, because of all these conditions you can prove. And then that's for because it's on R. So and because of compactness. So we did not need Hausdorffness. There was a proof with lesser conditions. There is, before going into that, let me see if I make the C. Yeah, it actually doesn't matter because you can just take mod, right? Because those are also valid functions. Yeah. Oh, no. Uh, yeah, in the case of C, it's, but then you don't know if, right, you can take mod, right? So you can easily show that if f is in an ideal, then mod f is also in the ideal because just multiply by conjugate, right? It's an ideal. So So those things. So this is fine. But you don't need compactness. So if this space is what is called, yeah, yeah, yes, because just multiply it with the conjugate of f, right? I mean, I'm sorry, modulus square is in the ideal. Yes, right. Modulus may not be in the ideal. Modulus square is in the ideal. Hmm? Yeah, and a modulus will also be there because it's a maximal ideal. Maximal ideal is a radical ideal. So then modulus will also be there. These things you can just note down and try it later. There, there is no idea there. Simple. But if we take what is called a paracompact space, that should also be enough. So let's just go to the new page. So if we take X P paracompact, define this. Maybe I don't actually know the definition, but basically I'm saying that there exists a partition of unity. So my point is that even if you have infinitely many of them, okay, if you have like, so xi square like this and I in I, any cover, then this will be positive, where this sigma I, this is a collection of functions. Okay, this is a, in fact you don't need to take square even, so it will be true even with some, if you try, if you want to think about modules over max modules or something like, yeah, you can, yeah, let's see. So so what are these sigma I? So these are what are called partitions of partition of unity. You can also read about this. So you, if you, yeah, if you don't know, I'll tell you the definition. So what this is. So basically this comes from the cover. Okay. So let's say you have this picture. So you have this space and then you have a cover. So it is basically a very important device to take averages. Yeah. So anyways, but I should cover it. Okay, so it's like we have a cover, could be finite or infinite. Then we say, so given a cover, so maybe I will write that here. Hmm. So given a cover U, okay, I in I, okay, rho I, this is called a partition of unity for that cover. Okay. This collection is called a collection of functions is called a partition of unity for the cover. More suggestive, and the official term is partition of unity subordinate to that cover, and there's the reason why they say that. Uh, so this is what. So these are basically, these rho i's are nothing but collection of functions from that topological space to R. So these are in CX such that uh, what do you say? I mean, image. So you see some kind of average. So image will be in 0, 0, 1. Okay. And yeah, summation rho I x is equal to 1 for all x in x. Okay. And there's one more condition which says that given any x, this is actually a finite sum. Okay. Meaning that all but finitely many of the rho i's are 0 for any point x. Okay. So this is just the, so do you get the intuition why this is a sort of an average? Right? Right? So it is some sort of a weight that you're putting on the things, on the UIs. Given any point, you are putting some, yeah, it's an average. Right? Okay. And there's actually one more, which is actually the important condition, which is which is not needed for us, is that the support, and you can read this, support of rho I, and this is why it's called partition of unity subordinate to this. These are compactly supported, and the support is inside UI. But we shall not need this. Okay. So now you see that this will be positive for every x, right? So I'm saying that, like, of course, here I'm just taking, if it's f, if f is sort of negative on around xi in a ball, then you just take minus f. So basically f of xi is, so we have the following. You have that f of xi is positive. I mean, f of xi, f xi at xi is positive. This much if you have, then you see that this will be positive from these conditions, right? Because you put any point, yes. Right? Yeah. So, yeah, maybe this I is a bit misleading, but you understand. I mean, I should have just said x, and this is just x in x. I don't need to worry about finiteness. Okay. So there is this paracompact spaces for which partition of unity exists, and this is the interesting things. I mean, very important things. So you can think about it, like, okay. But I would like you to think about one more thing. I don't think. I mean, I think that this kind of theorem is true without paracompactness also, or like it's true without this compactness or paracompactness assumption. I so basically, you know, Urizon's lemma from topology, you know, right? So see if your space is regular, so that's the term, right? Regular. So what was the hypothesis of Urizon's lemma? I think regular, and what was there any other was there any other hypothesis, or was it normal? Maybe normal. Normal is the correct. Yeah, regular is not enough. Right. So normal space. So maybe you should try to see what happens in the case of a normal space. Okay. X is normal. Maybe you can think and tell me later. Right. I think that if you have Urizon's lemma, you should be able to, or I'm not sure actually. So, anyways, I mean, okay. I mean, no. So what? Sorry. So what? Okay. Anyways, you can think about that. I'm not. I don't know. But I mean, what I know is there are many things here. This is like, I suppose, if it's locally compact, implies should imply paracompact, and that should also imply that thing. But again, those are things you can think. Those interesting things. But what? But now, if you further, so what have we done? We have shown that from X, you have a map to the maximal spectrum or the collection of maximal ideals of Cx, right? And this, yeah, there is this map, and it's in fact a surjective, right? So now you can show that if it's a normal space, then this is a bijection. Okay, so there is a bijection. So X, of course, goes to Mx, and this is a surjection from what we showed, but it's a bijection because basically the normal allows you to construct functions, right? So given a point, given 2 points, they will be separated by functions. Okay, so functions which vanish at those points. So yeah, and don't vanish at the other points. So that's what basically means separating, right? So given any 2 points, there will be a function which will separate the 2 points. Okay, which means that which basically that's a rough thing. I didn't. That's not a mathematical thing. You can make it formal. Okay, and that will imply that this thing is a bijection. Okay, yeah. So yeah, if the continuous functions separate the points of the space X, then it's a bijection. It's an injection, and if you have, as we saw, compactness, then it's a bijection. Then it's a surjection, and together it's a bijection. So this is all. This is the maximal ideal spectrum. We proved that. No, so that's right. Now, initially, that's what we proved, right? That for every maximal ideal, it's of this form. So that's surjection. Yeah. And if X is normal, I'm saying that that gives you injection. Probably also Hausdorff. Yeah, I mean, normal, then you assume that this Hausdorff was. Yeah. Okay. Then you get a bijection. Yes. Yeah. Say. You're right, I think, because compact Hausdorff actually implies normal. That's an exercise. Hey, that's true, right? You may have heard of that. That if a space is compact and Hausdorff, it implies normal. So you're right, I think. Yeah. So in that case, it also is injective. Compactness itself implies injective. Yes. Yeah. So that's interesting. Now I think you should think about this and see if you have more questions or if you already have. Yes. I don't know what happens to prime ideas. Yeah. Yeah. I don't think it can be described. So if you look at, even if you look at 0 comma 1, I don't think prime ideals can be described because, and prime ideals is a very strange, because then you are looking to go to all. uh, okay. Prime. Yeah, prime ideas could be many more because this is a ring. This ring is not any Noetherian or anything. So that is why. So do you have any example of a prime ideal which is not maximal? I mean, that is the, we can think about that first, right? Before thinking about anything else. Yeah, because you see, this is not a. This is. I'm sorry. Yeah, this is obviously not a. Uh, is not a domain. Okay, so zero is not prime. So how about intersection of two maximal ideas? Like if I take M0 intersection M1, no, this cannot be a prime ideal, right? This cannot be because that is like a general thing, right? That intersection of prime ideals with a prime ideal, then basically one of those prime ideals is that prime ideal, right? I mean, all of them are equal. That is a kind of theorem. So, yeah, at least for finite intersection, it is true. Yeah, so these are not there. So yeah, and so product will also not work. So what do you think? Since this is a question, I mean, look, there should be. Uh, no, I don't know actually. So, no. Uh, okay, there. No. Do you think there are prime ideals which are not max? Hmm. Okay. Vanishes at infinitely many points. Then, if it vanishes at all points and it doesn't give a prime ideal, yes. Oh, right. So are you saying that there are no prime ideals, other prime ideals? A function is not an ideal. You mean that will not be contained in a maximal ideal? It will be contained in all those maximal ideals for which it vanishes, corresponding to the points where it vanishes. It will be contained in those maximal ideals. Yeah, it feels like finitely generated ideas cannot be prime, but we can, yeah, just take this to be one. So it will be zero somewhere. So that's why I have the zero. One. Yeah, this problem could be interesting. I don't know. I get the feeling that there are no prime ideas. If you ask me, I get that feeling that there should be no prime ideas. Because hmm. Wait. No. Okay, I'm just changing the page, if that is okay. So if I just take this function, this thing, this ideal, is this ideal prime? Yeah, ideal generated by just fx going to x. Is this ideal prime? So, well, that basically comes down to just saying if x can be written as a product of two functions, right? Where both have some zeros. Both should have zeros at some points. Is that right? But that is obviously possible because you just take root x and root x, right? So yeah, so it's not prime. So this is how you see that this is a little right. So then you see that, I mean, you can do the same thing here maybe, or like of course then you can just see that uh, if it was over C then it is not prime. This uh, no, so there are problems because you cannot just take square root in C. Okay. Anyways, so I don't think going to C will make anything different here in this case. So let's think. Sorry. should be possible to write this as a product of two functions which are not uh, multiples of f. But how can that be possible if f vanishes at a single point? Then those two functions will also vanish only at that single point. So then if we take an example like this, so take a function like this, right? So can you write this function just for the sake of simplicity, we can just take that to be minus 1, 1. Yeah, can we write this function as a product of continuous functions? So this is again fx going to x. So can you write this as a product of two continuous functions? Where f and g are not invertible. That's the point, right? So f and g are not invertible, which means that f of g naught, sorry, just a moment. Someone called. Yes, yes, right. So, so they should vanish at 0. They should vanish at 0, right? You agree? Because they should vanish somewhere and they cannot vanish anywhere else. So they should vanish at 0. Yeah, it should be possible, right? Through some bad function, some other function is possible. Like, yeah, why not just, yes, okay, x like this. Okay, wait, that was okay or no? This, no. Wait, you are, no, so this function is fx equals to x. So you're so sorry. So your function, what function are you taking? X minus half. Okay. So let's say fx equals to x minus half, right? Then what do you suggest? F1 is this modulus, right? No, but then the capital F is my original function. Okay. Just a minute. Yes. What is the function? Yeah, but let's see. I mean, just take this only. Fx equals to x only from -1 to 1. That's what I'm taking. Yeah. Just see if you can find the function. Yeah. Yeah. Maybe you can take something like x by sine x times sine x. This one will work, right? Where you define this to be 0 at 0. Then this is both are continuous and the product is. Yes. So of course the idea was to remove the 0 of x somehow. Yeah. Or is there a problem with this example? No, no, no. So it's just C. Is there a problem with this? Yeah, there are problems. It's not defined at other points. Like it is fine because sin x is non-zero in -1 to 1. Yeah. Other than 0. So this is okay. Right? And so that's the point. And then you see that this so that's not a prime ideal. Yes. I don't. Yeah, but this will not help like mathematically extend this thing, but uh, yeah. So this kind of technique might help to classify like holomorph prime ideals in the collection of in a nicer collections like analytic functions or holomorphic functions, because there you can do some things like so there we have things like this. So suppose you're looking at analytic functions which are have a power series expansion around 0. Okay, so let's take all those functions which have a power series expansion from -1 to 1. Okay, and try to see if you can classify prime ideals there. Okay, because there you see there this maximal ideas that we got, they they um, they shall remain the same, right? If we take sort of compact list, then they will remain the same, right? Because the squaring and all will still keep it analytic function. Okay, means it will still have power series expansion. Okay, so there it will still remain. So the theorem will be true there, but then the good thing is that then the ideals will become principal, because if you have a maximal ideal, sorry, I should just say that. So if you have, let's say, analytic function f, okay. So if you have a f, let's say, function which has a power series expansion, right? then you know this kind of thing maybe, that if f of x naught is equal to 0, right, then it, right, yeah, then it means that f it means that fx is equal to x minus x naught times gx, right? Because the power series thing you can reason from there. So f has a power series expansion at x naught. So right, then you can do this kind of thing. Yeah. So yeah, that might be interesting. So you can think. But about continuous functions, I'm not able to say again. My hunch is that there are no prime ideas, but let me just check if yeah, prime ideas in. Have you checked online? Uh, yeah. So you see, this is a, yeah. So maybe I should share it with you. Yes. Each maximal ideal in ring of continuous function is this. Okay. And then for the prime ideal, I define, no, for each ideal, I define the zero set, but the map, this map. So now he's saying that you take ideals to their zero sets. Right. You take the ideal to the variety. Yes. Right. From ideals to closed sets is not an injection because two different ideals can go to the same variety. Uh, uh, right. Because for all x inside some closed interval which contains x naught, then uh, yeah, you can then check that this ideal also gives you the point 0, right? You can prove because you can take smaller and smaller closed intervals and take the intersection and so on. Yeah, right. This is definitely a book which I have heard of, but I've never studied it. Is this big enough screen? If you can read, are you able to read? Okay, okay. So former colleagues more knowledgeable than I am. No, but he's then asking for the ideal space. Yeah, ideal space might means if you take all ideals, then it should be maybe subsets because, but then also it is not a correspondence. Yes, for example, here's a counter kind of example. So take a dense proper subset. Yeah, so that um, doesn't work because yeah, dense subset will not give you a proper ideal. It will give you, means if you have a dense subset, it cannot be, it's the any ideal whose variety is a dense subset must be the whole thing because continue. So any filter of closed subsets of the interval. So filter of closed subsets should be a descending chain, I suppose, or because usually filters, if you see is defined on open subsets. Anyways, filter of closed subsets would then be just subsets, gives a proper ideal in say 0, comma 1 consisting of functions whose zero set lies in this filter. I don't understand how zero set. Okay, yeah, zero set lies in the filter means set in one of them. Indeed, the zero set of f plus g contains the intersection of the zero sets of this. So this is an ideal. Oh, so then by filter he means, yeah, so then I can tell you what a filter is, then what he means by a filter. Yeah, so this is could be interesting. So I mean, in general, you're trying to understand the ideals. Okay, right. So if you want to think about ideals and filters, yeah, so you should maybe basically you have to imagine what are the subsets or what collection of things in 0, comma 1 will help you to describe the ideal. You see the point, right? Like when you had maximal ideals, then only points were enough. But if you want to look at all ideals or all prime ideals, then you have to imagine interesting subsets or interesting subsets of subsets. Okay, to which you can draw some correlation with the ideals. So here they are talking about filter. So what is a filter? So if you take a collection of subsets, just maybe just here is closed subsets. So basically, you look at the collection of all closed subsets. Okay. Now a filter would be um, a subset of the collection of closed subsets. Okay. So you look at a subset which is just closed under intersections. Okay. So you take a collection of closed subsets which is closed under intersections. Let's say. Is that is that fine? So that's a filter. What's an example of a filter? Just take a nested sequence of intervals. That's a filter because it's closed under intersections, right? But you could have more interesting filters. Okay. Yeah. So filters and ultra filters and so on. These are very interesting objects. But so you see the point here. What he's trying to make is if you take a filter, some any filter, then he's saying that uh, if you take the yeah. So now you see now you take the collection of all functions. So you just imagine that you take these nested intervals. Okay, 0, comma 1, or minus 1, 1, minus half, half, minus 1 by 4, 1 by 4. Okay, take this. Okay, okay. So yeah, now you take all those functions whose zero set is in one of these filters. Okay, okay, yeah. But of course, this filter is not very interesting because if the zero set is in, I mean, then you're just taking the whole ideal, right? Whole ring actually, because you have taken minus 1 to 1. Okay. But if you take some more interesting filter, take just a collection of subsets which is closed under intersections. Okay. And then you take those functions whose zero set is in one of those subsets. Is that fine? Then you see this will form an ideal from his explanation. That's what he's saying. That if you say f plus g, because this zero set will lie in the intersection, but by the definition of filter, you have taken the intersection. Okay, so the zero set of f plus g will be in a closed subset, which is the intersection, right? But the intersection is also there. Okay, so yeah, there is small problem I see, but yeah, there are still some issues. But yeah, this notion could be useful. One has to think about it. So this way you get ideals, and these are called Z ideals. I suspect that there are conditions that every ideal is a Z ideal, but I'm not aware. So yeah. So yeah, I mean, you see, so these are interesting. So basically, you are able to capture more and more ideals through these interesting constructs, through these interesting constructions. Okay. Since this question came up to the front topic, mentioning that the excellent sequel, and this is rings of course. It's of course the subject on its own. It seems because you see people have written books on this and sequels of books. Since I was using anything, suppose every prime ideal in this ring is maximal. So they are saying that there could be something. So if every prime ideal is maximal, then what does that mean? So what does commutative algebra tell you? That if every prime ideal is maximal, then the ring has, yeah, then the ring has dimension 0, if you like. Okay, because there is a dimension, concept of dimension of rings, but what they're just saying is that then this is absolutely flat. And okay, if you don't know absolutely flat, it's fine. It's just, anyways, let me read and see where n is the nil radical. Okay, yeah, so nil radical, nil radical, but how could it, yeah, how could it have a nil radical? I'm very confused about this. Yeah, you see, like there are no nilpotents, certainly, right? In this ring. There's many interesting things. There are no in. That's another thing. I mean, there are no nilpotents, as you can see, because power of something function which is not zero will remain non-zero. So there are no nilpotents. But then he's talking about nil radical. So I mean, I'm very confused because nil radical is supposed to be collection of nilpotents. So, anyways, in a commutative ring, non-commutative ring it's different, but here it is where n is a nil radical, which is because he has written it. I'm sorry, yeah, nil radical is trivial. So this is absolutely flat. Okay, then for every f there is a g such that this. So this is the kind of thing I was trying to do, but of course I could not do this. Okay. Okay, but this is clearly impossible because of this example, which, yeah, so for this example, this is impossible. So there is no continuous G. So basically, there are prime ideals. You see? So that's what this example is saying. Okay, that prime ideals exist. If, I mean, so you have to study, you have to understand what these things mean. Then you can understand this. Okay, yeah. And so basically, from commutative algebra, you get that there are prime ideals because abstractly, if a ring doesn't have prime ideals, then it has some interesting things. But anyway, let's move to the answer. Here is a way to construct non-zero R. So here you see, but again, this will be just constructive because you have zones lemma coming. So anyways, I'm not saying it's bad or anything, but yeah. So you can try to read some of these things. There are many things here. Would be interested, but yes, this guy is an algebraic topologist. I know him, so I mean, yeah. Uh, so I think this paper may be some help, although this may not be the earliest source. So there that says that given a point P, one can find non-maximal prime ideas P1 and P2 such that this, the maximal ideal at P is a sum of these. Oh God, okay. So it's not intersection, but it's a sum. So then the ultra filters come. Okay, so it's, yeah. Yeah, so I mean, it's up to you. This is an interesting question. I don't know what you should do with this. Yeah. Why don't you decide which one you want to explore? Okay. Yeah, I'm not should not say anything. Yeah. Or you can try to just understand this one. Okay. Yeah, yeah, yeah. You can understand and yeah, I can't say anything at the moment. Yeah. to what you should try to. But since if it's a problem that you like, then you should pick it up and try to study it. I think that may not be bad. You can also look at these books if you have time. Okay. So I mean, yeah, you see, and then maybe next time if you want, we can discuss this further. Okay, that was just prime ideas in, yeah, in this. Okay, I mean, if you ask me, some one thing is the idea is not to know all these things, all of this, but the idea is to maybe pick one of the idea routes which you find interesting and try to follow it a little bit and see what you can do. Okay, yeah, okay, okay. I think that's I'll stop there because okay, yeah. It's an interesting, yeah, yeah. Thank you. It's an interesting question. Uh, yes. Okay, so that's it, right? We stop. All right. Bye then. Huh? Bye. So are we meeting on Tuesday? No, Sunday. If, yeah, yeah. It's up to you. Okay. If you see what you have done and so on, then you can let me know if it's or you want to tell me now. It's also fine. Uh-huh. So you mean next Saturday? Yeah. Tuesday. Tuesday. Huh, okay. That should be fine, right? Yeah. Okay. So that's fine. All right. See you. Bye.